Okay, Maureen, let's settle down here. Okay, let's settle down here. I know you just had an exam, so I'd have a shift of focus at here. So today is Halloween. I guess I'm going to tell you a spooky story here. And the title story is Triple Integrals. So we finished double integrals, so let's get on to triple integrals. Okay, so first, definition. So let's, okay. A natural extension of a double integral, basically, if you think of double integral is about integration over a certain region R in xy plane, right? Or a region R in a plane, basically. So now, when we are talking about the triple integral, it's going to be an integral over a region D, but now this is not going to be a planar region anymore. It's going to be a solid region. So we're looking at a solid here, which is basically a region, so we call that region D at here. Okay. So the difference between this region D and the region R of the double integral is, right, that's region R is a planar, it's a plane, only contains points x and y. So now it contains points x, y, z, right? Yeah. So now if I pick any point inside this region D at here, okay, region D here, then let's say I have a small volume, okay, I have a small volume around that point there, okay, small volume around that point. So let's call this small volume delta VI, right? Yeah, delta VI. So suppose I have application of this, okay, and I consider, okay, a function f x y z. Okay, consider I have a function x y z, which is defined, okay, over this region D. Okay, so define basically means you take any point from this region D, right, and then plug it into this function. You have a certain values for this function, right? Yeah. So that's mathematically what it means. Now I can think of this f here. So you can think this f, right, as, let's say, maybe density. Okay, so this f represents the density of this region D, okay, or a certain solid here, right? Yeah. So that's, for example, okay, you can think of it as a density. So then what we want to do is, let's say what's the mass, right? What would be the mass of this D at here? Okay. Or what would be the mass of the solid? Okay, so if I want to calculate the mass of solid, if the density is evenly distributed, right, then you have a density multiplied by the volume. That gives you this density, basically. Huh? Yeah. But if this density is not evenly distributed, it's a function, okay, is different at each point inside the region D, then it's not as simple anymore. So then what we do is, since I have this defined a small volume inside this region D around certain point, right? So I'm going to calculate the mass of this small volume. Okay, so the mass of the small volume here. Okay. First of all, the delta V, the delta Vi, right? First of all, delta Vi equal to what? So this is a volume defined around the point X, I, Y, let's say Z, I, right? Okay. If you think of this as a small volume, basically there's a delta X here, delta Y there, and a delta Z. Okay, so there's a very small variations around that point. So then my delta Vi, I can think of it as basically as a delta Xi, delta Yi, and a delta Zi. Okay. So that's the volume of the small box. This is the volume of the small box. Then the mass of this delta Vi is basically the volume multiplied by the density. Okay, so it's a small, so you can assume the density is even. It's not a variable for this small box. And what is the value of the density? It's F, Xi, Yi, Zi. This is the density, and multiplied by delta Vi. So that's the mass. Okay. So this is the mass for the one small delta Vi. But what you really need is the mass of the whole region D, which is the solid represented by the region D here. So then what do? We essentially add all the possible small masses, okay, inside this region D, right? So then total mass, so mass of D will basically equal to sigma F, Xi, Yi, Zi, delta Vi. Okay? Yeah. So you might have maybe n number of small volumes inside the region D, okay, if that's how you separate the region D. Okay. Then we're going to let, okay, n go to infinite. Okay, so we let n go to infinite. Then this summation in here will become an integral. Okay? So we got our mass of D, which becomes an integral. And it's a triple integral now. The reason because the delta V equals delta X, delta Y, delta Z. Right? And as n goes to infinite, this small delta will become just a D here. Okay, so that basically give us a triple integral, which is this. Okay, integrate over where? Over this region D. Okay, so this whole portion here, dx, dy, dz, it's essentially it's a dv. Okay, so delta becomes small d. Okay. This is basically triple integral. And as you can see, the only difference from a double integral is you just had one more integration at here, right? Integrating, and you had just one more variable at here. Right? So that's all the difference in here. Okay? Triple integral is, in my mind, is more useful than double because let's say you calculate mass. When we use double integral, we also calculate mass, but we calculate mass of a thin plate, right? Yeah, we consider thickness as as 0. But if you have any specific solid in actual system, it doesn't necessarily have a 0 thickness. So this is actually going to be the formula to calculate this mass. Okay, yeah. Triple integral. Any questions? Okay. Okay. So now the natural question here is, how do we compute or how do we calculate this triple integral here? So let's take a look at how do we evaluate this triple integral. Since what I write here is x, y, z, so the first step, just like the double integral, we're going to evaluate this triple integral in Cartesian coordinates. So basically, stick with x, y, z things. All right, so here's what I'm going to do. I'm going to draw some sort of arbitrary regions, all right, and then we'll go over the steps of this doing this evaluating the triple integral here. Let's move out a little here. Okay. So essentially, the number one step, okay, is to sketch this region D. Okay, sketch region D. So you might give in certain functions, but the first thing is sketch this region D first. So let's suppose I have a region D maybe look like this one here, okay? So maybe the region D is this thing here. Now this is a sort of a it's just simplified region D here, okay? So it's not necessary you always have a regular sizes, vertical sides here, okay? Now what happens is for this particular one, you can see that it's kind of bounded by a surface at the top and then bounded by a surface at the bottom here, okay? So let's say in this particular case, I have a surface upper bound, and here is, I call it z equal to f2xy here, okay? Yeah. And then up in the bottom here, it's a z equal to f1xy. So that's the top surface and the bottom surface. So you're probably giving here is the top surface, here are two surfaces, and the region D is what's bounded by the two surfaces, right? Then you can sketch the two surfaces, and then that'll be your region D. Okay? Yeah. So once you finish the sketching here, step number 2 is to determine the order of the integration here. Okay? So you have this dx, uy, dz. So basically you can do how many combinations? dx, uy, dz, or dy, dx, dz, or dz, dx, dy. So any combinations, you're fine, right? Any combination is good. Okay. So let's say I draw like this one here. I'm gonna do these steps here. Okay. So there's a reason I do this step because the sketch I have here. So I'm gonna do this dz, okay, dy, and dx. Okay. So which is order. Okay. So maybe I should write down this wording here. Okay, determine order, okay, of integration. Okay. So in this case, I'm going to do this order: dz, dy, dx. Okay, here's the order I'm going to do here. Okay. All right. So once you determine the order, okay, before we move on here, I need you to remember the idea of this integration here. Okay, when you integrate a single variable, you integrate from a to b. So what happens? You're sweeping from a to b, right? When you integrate a double integral over region R, then what happens is you try to sweep every corner of the region R. Okay, so now you have your integration is over this whole region D, which is solid in the 3D space. So the point here is you're going to do is you're trying to basically try certain ways to sweep through this whole region D at here. So that'll be the integration here, right? So we need to basically what show here is a method of sweeping through the region D, okay, or a method of creating this region D. So once we decided order here, now the next step here is, okay, you sketch the shadow. Okay, sketch the shadow, because you need this information here, okay? Sketch the shadow of this region D of the solid. Okay, sketch the shadow. The shadow, not arbitrary one. The shadow, you sketch the shadow depends on the order of the integration here. Now, since you decided on the dz, dy, dx, so now we're going to sketch the shadow in the xy plane. Basically, the shadow is on the last two variables here, right? So in xy plane. Okay, scatter shadow in XY plane. Is that clear? Yeah. So the shadow based on your decision of the order. Okay. So this is based on the order of integration. Okay. So in my particular case, let's say I'm dropping this one, basically project this solid into the XY plane, and suppose that I got maybe a shadow, let's say like this, right? I got a shadow of this. So in this particular case, the shadow of this one here, it's bounded by two curves. Okay, so I'm using this example. So it's bounded by two curves. This curve here, let's say this is a G2 of x, and this curve at here, okay, is G1 of x. Okay, so here's an XY plane. So this is y1, basically y equal to this, and this is y equal to that, right? That's two xy curve, xy function. All right, so that's the shadow. Okay. So once we finish this, now we're ready to do our sketching here. Okay, so step number 4. Okay, step number 4 is to find limits now, integral limits. Okay, integral limits. So let's see. Okay, remember what I said, huh? The idea is to try to sweep through the solid. Okay, sweep through solid. So here's what I'm going to do, trying to sweep through the solid here. I'm going to we're doing dz first, right? We're doing dz first. So the first one we're going to do is we're going to start from any point inside this shadow here. Okay, any point inside the shadow. Then you draw a vertical lines in the positive z-axis direction. Okay. So starting anywhere in the shadow and across this solid D, region D. That's the first step. So starting from a point in the shadow, okay, draw a vertical line upward, okay, across this region D. Okay, across region D. Now, this doesn't necessarily it means that you always just starting from this here, right? If a part of the solid is below XY plane, you still need to basically go across the whole region D, right? Yeah, go across the whole region D. Then once you did this part here, then this is basically more or less like the process in the double integral. So you can think of yourself, there is a stickman walking along this line upward. Then you will have a first contact and a second contact. Okay, first contact, second contact. So this vertical line essentially will intersect the solid region D by this much of line segments here, right? This much line segment. Remember the sweeping, right? The sweeping idea. So this is your first sweep. So the first sweep, you end up with a straight line, right? Straight line. And you have a first contact and a second contact, or you can see this is an inter point. That's the leaving point. Okay. Then my z mean, okay, is basically the first contact, and z max is the second contact. Okay, second contact points. All right, so now let's see what's my mean and max. So where does it hit? It hit the bottom surface here, right? Bottom surface. The bottom surface, the function is this one here. So which means my z mean is f1 bracket xy. then the Z max is F2 xy. Okay, yeah, so that's your first and second contact. Okay, which is basically the mean and the max of this segment of line at here. Okay, so then once you find this mean now, the Z limits now, then the next one here, because the next order is Y, so we need to find the Y mean and Y max, right? Okay, yeah. So find the Y mean, Y max, what you do is this. You draw, okay, you draw a horizontal, you draw a line, okay, in XY plane, okay, in the direction, okay, in the direction of a positive y-axis, okay, in direction positive y-axis. So here's what it means here. You draw a line in the xy plane. Basically, you draw this line across the shadow. Okay, so this line here across the shadow. Okay, across the shadow. So this shadow here, it's a plane here, right? So you can call this shadow as R here. Okay. So what happens is this is what you're doing. You draw this line, okay, like this. Okay, you draw it in the y positive direction across the shadow. Right. Then when you draw this line here, you can imagine, okay, there is another guy walking along this, walking along the line that you just draw here. And while you're walking here, imagine this line segment here. Okay, so this line segment is kind of like controlled by the motion of this one here. So then what happens is this guy will enter this shadow at here and leave the shadow at here, basically, right? Yeah. At the same time, you can imagine that line segment, right, is also moving. Okay, it's also moving there. So the motion of the line segment will basically sweep out what? Sweep out a certain kind of a cross section here. Does that make sense? Yeah. So you basically, this is sort of the second sweep. After this sweep here, you end up with a certain kind of a cross section. Okay, depends on the region. But we're looking for mean and max of y. So how do we determine that? We look at the first contact, the second contact of this line that you draw with respect to this region R or the shadow, right? So this is what happens here. Then the y mean, okay, is first contact, okay, of this line and the shadow R. Okay. And the y max is the second contact, okay, of this line and the shadow R. Okay. So let's say my particular case, this is the first contact, y is g1 of x. This is the second contact, so y is g2 of x. Okay, so that means this is equal to g1 of x. This means this is g2 of x. Right. So this is the second sweep. So first sweep, you got the line. Second sweep, right, you got a cross section. So that's not the whole region D yet, right? Yeah. So then the last sweep is, okay, the last sweep is then what do you do? Basically, you're gonna sort of moving this cross section back and forth, right? So while you're moving this back and forth, you sweep through, then you basically create this whole region D out here, the solid D. Okay. So doing that kind of action, it's equivalent to saying you're gonna sweep this line here, across this region R, across the shadow R out here, right? So basically, you move this one here across this region R. At the same time, when you're moving this one across region R, and that cross section that you just created because the second sweep will also be sweeping through this region D. Okay, yeah. So that's the last one step here to create the solid. and at the same time finding x mean and x max. So sweep, okay, maybe I'll call this second one, I'll call this line L here, okay, maybe line L. Sweep line L, okay, across this region R, which is a shadow. Okay, yeah. Find the bounds, okay, for x mean and x max. Okay. So the two bounds that you find in here will be constants. So you have this, if it's a simple region, then you will have an edge over one side and an edge over the other side, right? Okay. So let's say in this particular case, I didn't draw it here. Let's say in this particular case, one edge here is B, and one edge at here is A, right? So then my x mean will be A, and x max will be B. So that's it, right? With the three steps here, you created the solid. In other words, you integrate it over the whole region D, okay, without any corners being overlooked. Is that clear? Yeah. Yeah. So then you can lay down this integral here. Then my integral. So you have three integrals. Okay, integrate certain function over this region D. The order is what we choose is dz, dy, dx. Okay. And first limits for the z, we find is f1 xy, f2 xy. Right. The limits for the y, in this case g1 of x, g2 of x. For the x is a to b. All right. So that's it. That's our triple integral in Cartesian coordinates. Okay. Yeah. Okay. Now you got to be a little flexible here. Okay. Not necessarily you always choose this order dz, dy, dx. So sometimes the order that you choose actually based on the orientation, based on the shape of this solid, right? So imagine if this solid is not in this orientation. If this is rotated, it's oriented maybe 90 degrees like that, right? So I guess you probably won't choose the dz, dy, dx anymore, right? So you look at this one, which one basically will be easier to do this calculation. Is that okay? Yeah. So now let's take a look at an example. Okay? Let's take a look simple example right here. Suppose that we have this tetrahedron in here. When we wanted to calculate the volume, okay, of this tetrahedron, essentially with three sides of this x, y, z, y, and xz plane, and then this plane right here. And here is the point. Okay. Here's a plane here. Okay. Yeah. Okay. So if this is the question given in here, if the question didn't tell you what this plane is, right? I guess the first step is you need to figure out what this plane equation is, right? Yeah. So midterm, we have a questions on the line of planes. Final we want. But you still need to have the knowledge of getting lines or planes if possible. Right? So for this one here, it's actually quite easy. It's xy plus z equal xy plus z equal to 1. The reason is actually very simple. If you look at the edges of each edges, okay, in the associated plane here, the bottom line here is what? X plus y equal to 1, and this one here is x plus z equal to 1, and this one here is y plus z equal to 1. Okay, yeah. Okay, now we're trying to get the volume here. Okay, the volume of this guy here. Okay, so before calculating the volume here, even before thinking of calculating the volume using a triple integral, do you think you can calculate the volume using double integral? Right. If I want you to calculate the volume using double integral, what would that be? So double integral meaning it's this kind of format here, right? This kind of format. So then I'm integrating over a region R, integrate this function f here. So this function f, maybe I can think of the function as f as well as the height, right? As height. Height by area give you the volume, right? So in this particular case, let's see if I choose this as my region R. What will be the height? Which is what? Pardon me? What will be the height here? So if this is the region R I'm choosing here, what will be this function f? Exactly. So that will be basically 1 minus x minus y, right? Yeah, that's their top surface, yeah.
How did you get x plus y plus z equals 1?
Because this is 1 here, this is 1 here, so that straight line is x plus y equal to 1.
I got that one. The last one, x plus y plus z equals 1.
Oh, how do I get this one here? Well, okay, so if you go over the traditional way, what you do is you have this coordinate, you have this coordinate, you have this coordinate. What can you do? Can you create the two vectors here, right? And can you create the cross product using the two vectors? Yeah? Yeah. Huh? Solved? Yeah. Well, you got 100% in the 248 in the first question. You shouldn't have any doubt here. So anyway, the other quick way of getting this one here is this. You see this is a plane here, right? This is a plane. What happened when I let z equal to 0? It's what? X plus y equal to 1, right? When z equal to 0, meaning what? Meaning it's the intersection of this plane with xy plane, right? With xy plane. And you have the the intersection of two planes give you a line. So when you let z equal to 0, you get this line here, which is xy plus y equals 1. So that's when we basically verify this equation here, right? So if you come out with a different plane equation, and you let z equal to 0, and you find that the line doesn't go through these 2 points, that means there's something wrong. Okay? Yeah. So as I said, you can calculate the volume using this double integral here, right? You can double integral. So you have an upper surface, this is a function representing the height, and use your region R, you can calculate the volume. So now, if I have this triple integral now, so if I want to calculate the volume, basically what happens is I basically calculate this guy here, right? Calculate this. And all I set is I set this integrand f here equal to 1, right? Equal to 1 here. When it's 1 here, this triple integral gave me the volume, right? So in some textbook, actually, they don't write the 3 integrals, they just write 1 integral, okay? So with a d at here, okay? So that actually expressing the same idea here, right? Yeah. Okay, so if I choose this one here now, then the next logic question is I'm going to choose the order, right? So you already have this sketched, so we're going to choose the order here. So let's say I'm going to choose the order dy, dz, dx. Okay, dz, dy, dx. Okay. So here's my order. Okay. And you choose the order, meaning here is what happens, right? This is 1 and here. Okay. Yeah, we're going to find the limits for each one of the variable now. Once you get the order, the next logic step is what? To sketch the shadow, right? Sketch shadow here. And the shadow in this particular case in xy plane. So if you look at this one here, what's my shadow? Shadow is essentially this triangle here, right? It's this triangle. Okay, so that's your shadow here. Okay, so then now you're ready to pick any point inside the shadow. Then you draw. Okay, you draw a vertical lines across this region D. Okay, because you're doing dz first. That's why we do this step. Okay, we're going upwards. Okay, in the positive z-axis. So you have a first contact, you have second contact, and that gives you the z mean and z max. Okay. So in this case, z mean will be 0, z max will be y minus x minus y, right? Okay. Then you draw an arrow lines in the positive y-axis, okay, across this shadow here, okay, across the shadow. The first contact gives you y mean, second contact gives you the y max. So apparently y mean is 0. Y max is y minus x. Okay. Yeah. The last step, to sweep this line L at here across the shadow R, find the mean for the x, find the max for the x that bounds the shadow. So x will be 0 at here, and max will be 1. Right. So that's it. That's the volume calculation or the layout of this triple integral. Now, if I do the first integral, just do the first one here. You can carry out the integral here. Okay. So what do I have here? I have a 0. The first one here. Okay, I'm not going to do this. I'll do this one here. So I leave. I have what? I have 1 minus x minus y minus 0, right? And then dy dx. That makes sense? Yeah. So if you look at this one here, what's this guy? That's exactly the same as the double integral we were talking about there, right? Yeah. So basically, you can see that inside this bracket, right? What's inside the bracket is the upper surface minus the bottom surface here. The bottom surface is 0, so z equals 0, so there's nothing here, right? Yeah. So then, naturally, I mean, if this basically saying is, if you're calculating volume of a certain region, okay, D, if you're calculating volume of a certain region D, so you can either use double integral or you can use the triple integral. So which will all be the same thing here. All right? Yeah. Is that good? Yeah. So here is your upper surface, and here is the lower surface. So lower bound, right? Yeah. So if you have a solid, maybe the upper one is this guy, but the lower one is not 0. Maybe the lower one is something else, right? So then your lower one basically limits here, and then that minus that. Okay. Is that good? So try to calculate this integral yourself and see what happens. So take a look at the next example here. Okay, so here is a solid region D, and this point is 0, 1, 1. This point is 1, 1, 0. This point is 0, 1, 0. Okay? Yeah. Yeah. And we're looking for just in general, right? Just general. So we're looking for, let's see, a general kind of a triple integral here. Okay, general connect. So this is your region D here. Okay, your region D. And essentially, the practice is here to find the limits, okay, for x, y, z. Depends on the order that you pick. Okay, yeah. Okay, so when you look at this one here, and I want you to change the order of integration here, right? In the previous example, and also the general approach I gave is a dz, dy, dx, right? So I want you to do this one. You do this order: dy, dz, and dx. This order here. Okay. Yeah. If we do this order here, what will be the integral limits? So you have the solid D now. I guess the first step before you want to figure out this the limits here. What's the first step? Sketch what? Shadow. In which plane? ZX plane. So you project this whole thing into the ZX plane. So what's the projection of this whole thing in the ZX plane? It will be a triangle, right? So actually, it's this triangle here, right? It's this triangle. So projection, that means what the projection means here. So you got a triangle over here, okay? Yeah. Okay, if you got a triangle over here, so the next question is, what will be this edge of this triangle here? Because you're gonna need that, right? Yeah. What will be the edge here? So you can see now, this point here is 1, so that point is 1 there, right? And this point here is 1, so that point is also 1 here. So this edge here should be x plus z equal to 1. Okay. Now, I think I need a couple more information in here. First of all, okay. Yeah, before we figure out that, okay, let's draw the triangle here now, shadow. And the next step here is, if I do the y first, that means I'm going to draw a line across, pick a point inside the shadow, draw a line, right? Draw a line across the region D. So you draw a line across the region D in which direction? In the y direction, because you're doing the y variable first, right? And so that's what happens here. You draw across this region D here. Okay. So you will have a first contact here and a second contact here, right? Okay. And that'll be the y mean and y max. So y mean, y max, I guess y max is very easy. What's y max value? 1. Because here is the vertical plane here, right? And this actual plane y equal to 1. So anywhere along this plane y equal to 1. So the y mean is this plane at here, right? It's this plane. So that's actually maybe needs a little bit of work to figure it out, plane out. Okay, yeah. Again, actually, it's not that bad. If the plane in this case here, it draws the intersection of this plane with x, y, the axis and z, y plane. See, this is the intersection here. This is the intersection here, right? And this intersection right here is this is what? X equal to y, huh? And this intersection here is z equal to y. Okay, yeah. And the intersection of this plane with the plane y equal to 1 is this line, which is x plus z equal to 1. So you have this intersection of the plane with 3 different things. So you already, when you have that, you actually can nail down this plane equation right there. So this plane at here is y equal to x plus z. Okay. So let's see if this is right here, right? What happened when you let z equal to 0, which is, right? And what happened when you let x equal to 0? And that's the intersection. When you let z equal to 0, that's the intersection of the plane with the xy plane. When you let x equal to 0, that's the intersection of the plane with zy plane, right? And what happens when you let y equal to 1? And that's the intersection of the plane with the intersection of this plane. That's this line here. Okay? Yeah. So this is the plane right here. So in other words, my y mean would be basically, so maybe I'll write this layout of this double integral right here. Okay. So y mean is first contact this point, which is basically x plus z, right? X plus z. And y max is this point, it's 1. Okay. The next integration is about z. So then what we do is we draw a vertical line, okay, in the z-axis direction, okay, across the shadow, okay, across the shadow. First contact give you z mean, second contact give you the z max. So z mean is 0, z max 1 minus x. Okay. Last step is sweep this vertical line that you just draw here across the shadow here. Find the bounds for the x. Okay. So x is bound. The lower bound is not here. Lower bound is over there, 0. And upper bound is here, 1. Okay. So that's the layout of this triple integral, right? That's the layout of the triple integral. Okay, any questions? Okay. I think this Cartesian coordinate is fairly straightforward. Okay, so you just have to be very careful when you pick your order and when you draw the order. Once you pick the order, draw the shadow, and then start to draw lines, okay, with respect to different variables. Okay, any questions? All good? All right. Okay, so that's evaluating the triple integral in Cartesian coordinates, right? So then the next one here is just like double integral. You can also evaluate double integral using polar. But now we're in 3D space. It's a reading D, so we're going to evaluate this triple integral, okay, in so-called cylindrical coordinates. Okay, cylindrical coordinates. So first thing is, what is cylindrical coordinates first? So this is your xy Cartesian coordinates. Okay. Now I have a point at here, which is P. So if in Cartesian coordinates, P bracket x, y, z, right? So you use x, y, z to represent its location. Now instead of using x, y, z, we're going to use r, theta, z. So essentially, here is your P point projection at here. So this is your xy here, right? This is your xy here. Okay. Now we're going to draw. We draw a line. We draw a line here to here. Okay. Then the magnitude of this segment here is called r. The angle from this x-axis to where it is called theta. The height from here to here is a z. Okay, it's a z here. So the r theta z is basically cylindrical coordinates. If you compare to the polar coordinates, actually the only difference is you have a z here, right? A z. Yeah. In typical mathematics here, the cylindrical coordinates here, so you can think, oh, I must have some other coordinate. Yes, you do. You have a spherical coordinates. And you may have some other coordinates too, not necessarily just the 3. So basically, it doesn't matter what kind of coordinates here. So sometimes there's a general term here. It's called curvilinear coordinates. So there's a term called, okay, curvilinear coordinates. Okay, curvilinear coordinates. So what does that mean is basically, so let's come back to this cylindrical coordinates here, okay? Yeah. Well, look, this is your xy coordinates, right? This is your xy coordinates. Now, how do I represent the xy coordinates? If you recall that, basically you can use the key hat, I hat, and G hat to represent x, y, z coordinates. Okay. And in this particular case, this this I, J, K, they are what? They are orthogonal to each other, right? They are orthogonal to each other. So similarly, for this point P, if I don't want to use I, J, K, basically I don't want to express my point P in this x, y, z coordinates. So see, if it is 3, 2, y, 3, 2, 4, then what's the point P? It's a 3i plus 2j plus 4k, right? Yeah. So then I say is, okay, I'm going to use the polar coordinates. Then you basically have another set of a coordinate system. So this set of coordinate system for this one here is this. Here is this direction. This is called ER hat. So this ER hat is in the direction of R, increasing R direction here. Okay. And you have another direction here. This is E theta hat. So that's in the direction of increasing theta. Right? You can imagine if they are here, when you increase the theta here, that vector will be perpendicular to this vector here. Okay? Yeah. And this E theta together, using right-hand rule, is going to be your EZ. So you can imagine there is a coordinate system attached at this point here, okay? And that's basically the so-called polar coordinate system. For polar coordinate system, you have this polar coordinate, which is R theta Z. Is that clear? Yeah. So I'm not going to go into too depth here. Basically, if you look at the two coordinate system, right? To look at two coordinate system, there is a connection between the two coordinate system. Okay. Basically, what's the difference between the two coordinate system? If I shift this coordinate system from here to here, right, to make them sharing the same origin, can you visualize what's the difference between the two coordinate system? Not necessarily 45. It's just rotated by which axis? By the z. How much? Theta, right? That's the only difference between the two coordinate system, right? So essentially, the two coordinate system can be related to each other by a so-called rotation matrix, right? Yeah. So we're not going into too much depth here, but there's a connection here. In other words, okay, if I have a point P at here, if I got a point P here, I can always express the same point P in a totally two different coordinate systems, right? I can express the point P in this coordinate system, and I can express the point P in this coordinate system. So they're all good, right? They're all good here, right? Okay, so now come back to this R theta here. First thing is what we need to do is, what is the connection between this R theta Z and this original X, Y, Z? Okay, yeah, that's what's in here. So that's actually quite simple here. So what's the connection between R and the X? So you can see now, basically what? The X equal to R cosine theta, right? And the Y equal to R sine theta. And Z is not changing. Z is still Z. Okay. So that's a connection between the two set of coordinates at here. Okay. Yeah. So now mathematically, okay, as I said, not necessarily it's going to be Cartesian or cylindrical. It can be any other so-called curvilinear coordinates. So in general, sometimes you can use Q1, Q2, and Q3, okay, to represent a general curvilinear coordinates here. Okay, but there's one common thing though, very common thing. One common thing is, okay, think about this. In Cartesian coordinates, when you set one coordinate equal to a constant, for example, you set x a constant, what do you end up with? you end up with a, you set x to constant, meaning it's actually what? A plane, right? It's a plane. You set y equal to constant, it's also a plane. You set z equal to plane, it's also a plane. But let's consider it's a surface, right? Basically, you set that as, you set the coordinates equal to constant, you end up with the surface. Is that good? Right? Same rule apply to any of these curvilinear coordinates. You set q equals to 0, you end up with the surface. You set q2 equals 0 or q3, you end up with the surface. Surface not necessarily a plane. It can be a curved surface. Okay? Yeah. So now let's look at this one. This is my cylindrical coordinates. What happened when I set my r theta z to constant? What kind of surface do we have? Let's say, for example, right? If I set r equal to a certain constant r naught, what kind of surface do you have? Cylinder. It's a cylindrical surface, right? Yeah. So basically, in cylindrical coordinate, you said r equal to constant. You actually just means it's a cylindrical surface. Okay, up and downs to infinite and negative infinite to positive infinite, right? So this is a cylindrical surface. Okay. So how about if I set theta equal to a constant? What do we have? Plane. Is it what kind of plane? It's actually, well, it's theta constant, meaning maybe it's right here, right? It's actually half plane, right? It's half plane with one side of the edge where at this z-axis. So it's when you set this theta equal to 0, basically what you have here is it's like a plane like this, right? It's half plane like this, right? Yeah, that's theta equal to 0. Okay? Yeah. So if you set theta equal to theta naught plus pi, you're actually referring to the other half of the plane, right? Yeah. So what about z equal to z naught? It's a plane, yeah. It's basically horizontal plane, right? Yeah. So that's the same idea here, okay? Same idea. So you for any set of a coordinate system, okay, you set the coordinate variables to be a constant, you end up with a surface. So it can be a plane. The surface can be a plane, or the surface can be in the future when we have that spherical coordinates. The surface can be simply a sphere. Okay, the surface is a sphere. Okay. 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 So that's good. Now the next logical question here is, don't forget we're trying to evaluate the triple integral in polar coordinates, in cylindrical coordinates here, right? Yeah. So your triple integral in Cartesian coordinates is, let's say I use this one here, okay? It's this, okay? Now we're not going to use an x, y, z anymore. We're going to use our variable r theta z, right? R theta z. So just like the polar double integral here, so what we need to do is, okay, number one step, we're going to change this x, y, z in the function f into the corresponding polar coordinates. Okay, that's what we're going to change it here. Okay, that's what we're going to change. And this dx, dy, dz has also to be changed. But then the whole question here is, what's that going to be changed into? Is that going to be just simply dr, d theta, dz, or maybe something else, right? Yeah. But I guess you will have this dr, d theta, dz here, right? The only thing here is, do we need to multiply anything at here or not? Okay? Yeah. The point here is you're not going to change this thing here. So this is a dv at here. So this whole chunk at here should also be a dv. Okay? Should also be a dv. Now I do have a different ways of deriving this one here. So let me show you this approach here. Basically, this is using a limits concept here. In Cartesian coordinates, when you calculate dv, you take a box, right? You take a box to approximate a certain small volume. But in cylindrical coordinates, so what you do is, okay, instead of using a box, we're using a shape like this. We're using a shape like this. So this is essentially this is a part of the circle, and this is a part of circle, this is part of circle, right? And this is a part of the reading lines, this is a part of reading lines here, okay? So it's like you're separating your a certain kind of cylinder, okay, using a whole bunch of clustered, okay, cylindrical objects, and your intersects having a small objects like this one here, all right? Yeah. So for example, I can call this is R here, and this is portion here is going to be delta R, okay? And this portion here can be called delta theta. So there's a small rotation. This is Z here, okay? Yeah. And the height set here is delta Z. Okay? It's delta Z. So that's a way of approximating a small region, the volume of small region here, right? Because it's small, so I can think of this as I can think of it as a rectangular box. Okay, I can think of still this box here. So then the volume basically is the area at the bottom multiplied by the height, right? By the height. So what's the volume of the area at the bottom here? It's this side multiplied by this side here. And this side is delta R. And what's this side here? It's R d theta. So basically you have R delta theta, which is the bottom volume, bottom area here, and multiplied by delta Z. That's dV, okay, or delta V. Okay, that's delta V. Okay. And then when you have a very, very small delta here, so this guy basically turns into dV equal to R dr d theta dz, right? Okay. Now this is what we're going to replace here. So this guy here, okay, instead of just dr d theta here, you actually has one more R at here, okay, one more R. So is that clear? Yeah. All right. So this is how you end up with the transformation, okay, from Cartesian to polar. Okay. Now I'm going to tell you another way of doing this one here. This is the way that I'm going to tell you now is actually a much better way of doing it. This is called using Jacobian. Okay? Yeah. Yeah. So this is optional here. Okay. Yeah. So. Have you heard of Jacobian? Yeah. Yes. Where? Numerical method. What's the Jacobian doing over there? Just a matrix, right? Yeah, exactly. So basically, we're talking about Jacobian matrix here. Now the Jacobian matrix here is this. You see, we have R equal to R cosine theta, Y equal to R sine theta, and Z equal to Z here, right? Yeah. So you consider the three things that are here as three functions. Okay, three functions. So this is a function of R theta Z. This is a function R theta Z. And this is also a function of R theta Z. Okay? Yeah. Then we're going to be able to form our Jacobian matrix, which is dx over dr, dx over d theta, dx over dz. Is that the same way as you have in your numerical analysis? Yeah, good. Then dz over d theta, dz over dr. Okay, so this is a Jacobian matrix. So Jacobian matrix basically it's a first order partial derivative of a certain vector value of functions. Okay. Yeah. Okay. Then if I plug this x, y, z over here, okay, plug it into this one here. So what do we get? Okay, so this is actually quite simple. R theta dr. So let's get cosine theta negative R sine theta 0 sine theta R cos theta 0 0 0 1. Okay. Yeah. Okay. So now you got this Jacobian matrix. But what we need is we need the determinant of this Jacobian matrix. Okay? Yeah. So let's call this as a J matrix here. Okay. So now I'm going to use what's the determinant of this J at here. So you know how to calculate determinant. So 3 by 3. If you do this determinant matrix calculation, you're going to end up with basically R. Yeah. So see, this multiply this, right? This multiply this is R squared cosine theta squared. And these two are all 0. Actually, you only have the other one here. And there's this minus this to multiply this. And minus minus become positive. So altogether you get R here. Now then your transformation in here essentially, you see that dx, dy, dz is basically equal to this determinant of j, dr, d theta, dz. Okay? Yeah. So that's very useful. Okay, very useful. So one of the additional questions I'll give you guys is you probably will use this one here. Okay. Sometimes you can have a totally different curvilinear coordinate system instead of just a polar here, right? Yeah. But you can do a little transformation of these variables. Transformation of the variable using this concept here. Okay, it's very useful. As a matter of fact, this Jacobian matrix here is this is 3 by 3, right? So basically, this is the function f. Okay, this is the function f of r theta z. It's like a function f r theta z, which has 3 functions. One is x, one is y, one is z. Okay. So what happened when this matrix has only one row? What do you get? What's this one here? We learned that's del, which is gradient, right? Yeah, that's the gradient of function x here. Okay, yeah. Okay, so let's take a look at the example here. Okay. You mean this one here?
Left side.
Oh yeah. Thank you. Okay, so let's look at this example here. Okay, there's a region. Okay. Bounded by z equal to x squared plus y squared, and the z equal to 4 minus x squared minus y squared. And we try to calculate the volume. Okay, calculate the volume this way. So first step is to sketch. So usually sometime in the question I'll give you the sketch, but I think you should have some of the essential skills of being able to sketch this out. Okay. First thing is z equal to x squared plus y squared. What's that? That's actually a paraboloid, right? Paraboloid, and the minimum value of that is 0. So it's okay. That's a surface like this. Is that good? Yeah. And the second one here, this is 4 minus x squared minus y squared. So the maximum for this guy is actually what? 4, right? It's actually 4. So this is also paraboloid, but it's upside down. So maybe it's more looking like so let's say this is a number 4 here. Okay. So you're going to draw a paraboloid, okay, which looks down here. Okay, which looks down. Okay. So there are two bows on top of each other, okay, and we're looking for the volume, right? Yeah. So I guess there's going to be an intersection here, right? There's going to be an intersection. So the intersection is right here, right? Yeah. Okay. So once you figure this out now, okay, And I guess the next question is, actually now you have a two different coordinate system. The next question actually is which coordinate system shall we use to calculate this one here, right? Yeah. If you can't see it through that clearly, you can always use the Cartesian coordinate to carry this out, right? So let's try the Cartesian coordinates, right? And see if that's going to work. Okay, in Cartesian coordinates. Okay, in Cartesian coordinates here, we draw it already, and we decide on the order of integration. So let's decide on dz, okay, and dy, dx, the traditional order. Okay, yeah. So if I want to decide this one here now, then the next thing is I'm going to have to draw a shadow, right? To draw a shadow of this solid in xy plane. So what's the shadow of this guy in xy plane then? Yeah, it's a circle. So it must be this shadow of this guy here, right? So it got to be this thing here. Okay, it's got to be this. Okay. Okay, so if this is a shadow here, I guess now you need to figure out, okay, what's the circle? What's the equation for this circle here? That makes sense, right? You need to figure out this equation of the circle here. Okay, so what's the circle? What's the equation of the circle? Pardon me? And maybe the question is, where is this circle created? It's created by intersection of this one and this one here, right? So in other words, anywhere along this circle, the points there must satisfy both of this equation here. So the z points, so they all have the same height, right? They all have the same height. So that means this x squared plus y squared has to equal to this one. Okay, so the x squared plus y squared got equal to this one. Okay. So then, what's my circle here now? You move this over there, so you got 2x squared plus 2y squared equal to 4. Then you divide it by 2, so you end up with the square, which is this one. Okay. So that's a circle with the radius of a square root of 2. Good? Yeah. Okay, so then the next thing is quite simple now. So what you do is you draw a vertical line, right? You draw a vertical line. This is a shadow. You draw a vertical line through the shadow, okay, through this region D, right? Through the region D, and try to find, my drawing here. Try to find the mean and the max from the first and the second contact. Okay. So what's the first and second contact? So Z mean is the bottom surface. Right, so when you draw up, it hits the bottom surface first, which is this one. So Z mean is this. Z max is the top surface, which is this. Okay? Yeah. So that's your Z mean, Z max. And then we try to find Y mean and Y max. To find Y mean, Y max, what we do, we draw a horizontal lines in the y-axis direction. So maybe I'll draw the shadow here in the xy plane. And that line is basically this, right? That line is this. So where does it hit first? Hit here first, then hit this next, right? So this is your y mean, this is your y max. So what is y mean here? And this is the bottom half of the circle. This is the top half of the circle. So bottom half of the circle is, so if you say this, yeah, so negative 2 minus x squared, right? And the y max is positive. Okay? And the last step, sweep this green line here across the shadow, find x mean and x max. So x mean is going to be negative, what is it? Root 2. Okay? Yeah. Okay, so once you figure out now, you need to carry out the triple integral here. Okay, if I carry this triple integral out, let's see how complicated it's going to be. Okay, that's the layout. So let's see what we have. First, this integral. So this integral gives me this minus this. So that's 4 minus 2x squared minus 2y squared. dy dx. Not bad, right? That's not bad. Okay, yeah. Okay, so then the next one here is what becomes more complicated now. So this is the y, right? So there's no y, there's only y and y here. Okay, so you're going to end up with this 8 2 minus x squared 4x squared 2 minus square root of this. Okay, you're going to end up with this. Okay, yeah, not bad either. But it's the problem is from here, that's going to be a big question mark, right? It's a big question mark. So I don't think anybody would like to do this integral during exam setting. Okay, yeah. So the whole point in here is, okay, not to do this integral. The whole point is just to point it out. The choice of this coordinate system, okay, doesn't matter. Okay, so is that good? Yeah. So we're going to show how to carry this one here using polar in the next lecture. Okay? Not polar, sorry, cylindrical.